Welcome back. And the session today is a continuation of what we discussed yesterday. And it's going to be a session which will be dedicated to different contributions to perturbation theory. These are mainly given by whiteboard notes. The material which you can look up when it comes to many of these discussions is something which is covered by chapters 4 to 6 by Shavit and Bartlett. We will continue with this topic next week as well. And one of the things which we also will be doing today is to start discussing diagram rules, which will give us a very powerful tool for setting up analytical expressions for different contributions order by order. And then we can also visualize many of the contributions to given orders and interpret them in terms of specific physical correlations. Now, what I want to do now is just to bring back the whiteboard and bring us back to some of the elements which we discussed yesterday and in connection with the interpretation of many-body perturbation theory and its link with full configuration interaction theory. So let's switch to the whiteboard and try to look at and deepen some of the arguments which we made yesterday. So yesterday, where we ended was with a discussion of a second-order term in many-body perturbation theory, which was due to what we called one-particle, one-hole excitations. So let's take a look at where we ended yesterday. So one of the topics which we discussed was first the correlation energy when we did FCI theory. So if we now look at the correlation energy from FCI, which is given by E0, the exact energy for the ground state, minus the reference energy, and this involves the expectation value of the Hamiltonian for a given reference state. This was in FCI theory given by, and this is an expression which is valid for all types of interactions up to two-body types of interactions. So we had a sum over one particle, one hole correlations, and we had the coefficients which we get when we diagonalize the Hamiltonian matrix. And then we had the integrals, which then involve the so-called Fock operator, the Hartree-Fock operator. We define this term F to consist of the non-interacting part of the Hamiltonian plus the correction to the motion of the particles due to a mean field which is set up by all the other particles. And then we had the term which came explicitly from the two-body interaction without having rewritten the interaction in terms of a one-body and two-body term. So this is just a pure two-body part of the interaction. And again, these coefficients were coefficients which we would obtain by diagonalization. Now, what we did in perturbation theory then was to define a new correlation energy, which we can label with MBPT. And in this particular case, it's still the ground state which we are targeting. But then this is given by the difference between the non-interacting energy and the true energy. And in this particular case, we would then have the first order term, which we labeled like this. So in the first order term in terms of the interaction. And then we had the higher order terms of delta E0 of 2, which is second order, plus, plus, plus. And this goes in principle to infinity. Now, what we did yesterday was actually to calculate the two-body term. So let's quickly remind ourselves, not the two-body term, but the second order term. So yesterday, we looked at delta E0 to second order, and the interaction which we have, this H of I, defines then a contribution over intermediate states, where we now have the integrals which connect the ground state with an intermediate state phi lambda, and this is multiplied with phi lambda And these states run from 1, because we have only singled out one ground state. This is our effective Hilbert space now. And the sum goes up to infinity in principle. And then we have the matrix elements, or the integrals actually, of phi 0. And this is divided by epsilon 0. So we are using Rayleigh-Schrödinger perturbation theory minus the non-interacting energy for the state phi lambda. So let me just quickly correct this one, because this is going to be a 0 here. Now, what we have then is that these states phi lambda could then represent either a one particle, one hole state. So we have the sum over all possible one particle, one hole excitations, or we could have a two particle, two hole excitation. And these are the only possibilities which we have, since we are dealing with a two-body interaction. So this H of I now is the two-body interaction, and can be the two-body interaction, or it can be the one-body part of the interaction, which comes from the normal ordering with respect to the new vacuum. Now, the terms which we looked at yesterday then was the one which was due to the one particle, one hole part. So let's now look at or just remind ourselves of the one particle, one hole contribution. That gave us a contribution to the energy, which looks like A or I, so the sum of a particle hole states. And then we had the matrix elements, or the integrals, which then involve this operator, which we defined as a Hartree-Fock operator. So I'm going to set it up again. And then A, and then we have an A and U Hartree-Fock, and I. And then the difference in energies result then in a epsilon I, the whole energy, which we're looking at, minus the particle energy. That's the single particle energies. So we have moved from, and hopefully you can see that this is an uppercase epsilon. This is supposed to be a lowercase epsilon. So this is the energy of a many-body state for the non-interacting case. This is the energy for the given excited state, which could be a one particle, one hole, a two particle, two hole excitation. And these states here are the many-body states, whereas these are the single particle energies. So this is the term. And when we then go back to the expression we had from FCI, we see now that when we make the comparison here, in FCI, let's now just bring back the FCI term. So the one particle, one hole piece from FCI is a term which runs like AI. And then we have the coefficient, which we get from diagonalization. And then we have the term with F of I, like this. Now, what we said yesterday is that if we have assumed that F as an operator is given by this H0 plus this U Hartree-Fock, and if the basis which we are having, which is a pretty common assumption in many-body perturbation theory, if the basis is so that these states A and I are eigenstates of H0, so we have an epsilon A times the state A, and then we have H0 of I, and we're also assuming, as always, that this is an orthogonal and normalized basis. Then the H0 term disappears. So what we get then is that this sum, if we now just mark out these terms here, so this term here becomes something which is close to what we have here. It will include this part. And then what we did yesterday was to identify this coefficient in many-body perturbation theory with this term which we have here. So let's now remind ourselves again about it before we move on to the case with two particle, two hole excitations. Okay, so let's look at the equation which we had from FCI. So the FCI equation gives us, for the one particle, one hole guys, it gives us a summation over the particle and hole states. Remember now that we have moved from the overlaps or the transition probabilities of a many-body state to another many-body state. And we have, due to the fact that the many-body states are expressed as functions of single particle states, like a Slater determinant, which is our choice of a trial wave function and computational basis, then everything translates into a sum of single particle states. And for FCI then, if we assume that that basis is an eigenbasis of the non-interacting part of the Hamiltonian, what we get then is an integral which looks like this. Well, we have this Hartree-Fock potential, which I'm going to remind you of just in some few moments. If we look at many-body perturbation theory for the one particle, one hole type of excitation to second order, what we have then is a summation over AI, and then we have I of U Hartree-Fock of A multiplied with A of U Hartree-Fock of I divided by epsilon I minus epsilon A. So what we see now is that the CIA from many-body perturbation theory, so this is actually the correction to the wave function, is given by I of U Hartree-Fock of A divided by epsilon I minus epsilon A. And this is going to approximate the coefficient which we get from FCI. So this is an approximation to CIA from FCI. Now, when we now are going to look at the two-particle, two-hole term, we are going to get something which is similar, but except that the term in both the numerator and the denominator are going to be different. Now, let's take a closer look at the expression we had, because yesterday I think I forgot one term here. So we're assuming that the parts here are emission, but let's now just remind ourselves about the definition of U Hartree-Fock. So this term here is now simply given by a sum over the states below the Fermi level. And then we have an anti-symmetrized matrix elements of the two-body interaction. And then we have an AJ anti-symmetrized. So that means that if I plug this expression in here, I'm going to get a double sum, because this term here contains a sum over j's, but then this term here contains also sum over j's. And since we are just multiplying these two terms, the final expression for many-body perturbation theory to second order, and I think I did something wrong yesterday because I just took and squared these matrix elements, but the final term with a one particle, one hole excitation type of intermediate state. So let's just label this as a one particle, one hole. That is going to be given by a summation over A and I, and then we have J and K. So we will get a term which goes like IJ, V, AJ. But now we have the second term, which is given by a summation over K. So we have IK. So these are anti-symmetrized matrix elements. And I have V, and then I have AK here, divided by epsilon I minus epsilon A. So later today, we are going to see how we can express this in a diagrammatic form. So the point now is, as we ended yesterday's lecture, is that the terms which we get in perturbation theory give us a correction to the exact, if we can diagonalize, it gives us a correction to the exact coefficients which we get from diagonalization. So these are the eigenvectors which come out when we diagonalize the Hamiltonian matrix. So we can then, order by order, construct a correction to these terms. So in principle, we should go to infinite order, but the hope is obviously that if we stop at, let's say, second or third order, we are getting pretty close to the exact expression. So in the second midterm, you will actually compute these terms to second order in interaction, and compare them with exact diagonalization, just to see how the difference, what kind of differences you have. And in particular, what you will see is that the difference is very sensitive to the strength of the interaction and the spacing between states below and above the formula. Okay, so what we're going to do next now is to look at the term which arises from the two-particle, two-hole intermediate state. So this is our next term. So as I said, we can only have two types of intermediate states to second order. We can have a one-particle, one-hole excitation, and then we can have a two-particle, two-hole excitation. So if I take the two-particle, two-hole piece, what we would need to evaluate then is the following. So MVP2 to second order, but now we are looking at the two-particle, two-hole term. And now what we have is an expression which is going to look like as follows. So we are going to have 1 divided by 16. And we are going to, so this is going to be the interaction which we have. We are going to have a summation over the intermediate states, which I haven't specified yet. And we are going to now calculate pi 0, and we will have the two-body interaction. So in this particular case, we're going to have an AP summation AQ, AS, AR. And this is now acting on a state phi lambda. I'm going to add to my summation the sum over these specific single particle states. But then we're also going to get a new term. So I need a summation over V and W here, because this one is now multiplied with, I'm going to have a phi lambda, and I have a similar matrix element contribution from the two-body interaction. So each one of them gives a term of 1 divided by 4. So then I would have an AT dagger, I will have an AU dagger, and then I'm going to have an AW and an AV. And then it brings us back to the ground state again. This is then divided by epsilon 0, the non-interacting energy, epsilon lambda, the non-interacting energy of the intermediate state, multiplied, and then we have this given integrals. So we are going to have the integrals over PQ, V, and then we have RS, anti-symmetrized, and then this is multiplied with TU, V, and then we have the final term, V and W. And this is also anti-symmetrized. So we are plugging in the interaction, which we are dealing with, which is now a two-body interaction. And then we need to calculate these quantities here. This quantity and this quantity here. So just keep in mind one thing, that this state now is the same as the state which we have here. So that means that when we pick out a specific two-particle, two-hole state, then we need to look at the same state here and the same state here. So that means that when I perform the contractions now, these contractions will put a constraint on P, Q, S, and R, and you're going to see that T, U, W, and V will have to be the same here, because the state which we are looking at, this intermediate state, is the same in this integral as it is in this integral. So let's look at just these contributions which we have here. And let us now look at a given state. So the state lambda here goes now over to a two-particle, two-hole state. And that means that we're going to have a Slater determinant IJ, AB. And there is a small thing now which we have to be careful with, which we're coming back to, is because we are setting in an operator. So we are going to set in, so this state with this one is actually now going to be a two-body operator, because it's given by two correlation and two annihilation operators. And since these are fermions, we would have to anti-symmetrize it. But let's just leave that for a small moment out of the calculations, and let us now just look at how we set up this term here. So we would have an A dagger, A B, and AJ, and AI. So this is what we have seen before. Let us now go back to one of these expressions. And what we could do now is simply to just pick either this term or this term. So let's just pick this term which we have here. And let's start looking at the contractions which we can have. So we have phi 0. And we're now just going to look at the creation and annihilation operators. And we're going to leave the other terms out of the calculations here. And then we have an AA, AB dagger, AJ, AI acting on phi 0. So I forgot one thing here. So this should be multiplied with phi 0. Sorry for that. Now, if you now look at this, and this is something which we have calculated already, there are only 4 possible sets of contractions which are giving something which is non-zero. So one of the contractions which we can do then is obviously this one, and then we can contract this with this one. And clearly we can do Q with J, and we can do P with I here. So this is going to give us 4 Kronecker deltas. I'm going to have a delta P of I. I'm going to have a delta Q of J. I'm going to have a delta S of B and a delta R of A. This will now give us an integral. So the final integral which we have to include in the calculations. So we put in a constraint here with the Kronecker deltas on the summations of a P, Q, S, and R. So this gives us now an integral which we need to either evaluate or tabulate. So this will be AB, IJ, anti-symmetrized. So that is one possible contraction. And then we can start playing the same games which we did before, and we get 3 more. So one is just to keep these guys fixed, the whole lines, but then we can interchange the contractions in the particle states. So we would then have this one going like that. And the 2 outer ones, the ones involving the whole states, are going to be the same. So we will get a delta P of I, a delta Q of J, but then we're going to get a delta S of A and a delta R of B. And that will give us a minus sign because we have to interchange the positions of 2 creation operators. And this gives us a contribution which is going to look like this, IJ or V, and then we have a BA, anti-symmetrized. We know, however, that these anti-symmetrized matrix elements are then given by this relation here. So this is given by AB, anti-symmetrized. So that means I get 2 contributions. And in order to make a long story short, because we have already calculated this when we looked at Hartree-Fock theory and also the specific integrals which we had to put in to the Hamiltonian matrix. Then we have 2 more contributions, and this is pretty obvious to see because now we can interchange the whole states. So we could let P, instead of going to I, we can let P go to J, but then we would have Q to go to I. Then we have to interchange these 2 operators. That gives rise to a minus sign. We could keep this ordering here, and that will give us an integral which looks like this one, except that we will have AB, but then I will have JI here. And then finally, I can now look at P going to J and Q going to I, and then I can change S going now to A and R going to B. And that will give me an integral which will be JI and BA, which is exactly the same as this one. So that means I will get 4 terms. So these 4 terms will take out one of the 4s here. Now, however, if you look at this term here, that will give a similar contributions. So keep in mind now that when you look at this specific term, this one, the state which you have here is exactly the same as you have here. So when we then are performing the contractions, when we now got that P had to be equal to I, Q to J, etc., etc. We are now going to get that T has to be equal to I, V to J, etc. So that means that the 8 double sum here is going to be simply reduced as summation over the states A, B, and I and J. So if I do this now without considering the fact that this one multiplied with phi lambda is actually an operator, what we are going to get then is the following. So if I do this, I will now get an expression which is given, so my delta E zero for second order of the two particle, two hole types of excitations is now going, since I get two of these interactions 4 times, then this is going to be given by a sum over A, B, I, and J. And then I will get these integrals of V, A, B, and then multiply with A, B, these are anti-symmetrized, and then V, I, J, anti-symmetrized, and then it contains the denominator, which is now given by the non-interacting energies of the ground state minus the non-interacting energies of the two particle, two hole state. So if I take the two particle, two hole state, that is going to be equal to epsilon A. So hopefully you can see that this guy here is supposed to be an uppercase letter, and this is going to be a lowercase letter. So I have epsilon A plus epsilon B minus epsilon J minus epsilon I, because I'm taking away these hole states, plus epsilon 0. So when I plug that into the denominator, then I'm going simply to get the difference between the hole states and the particle states. So this expression then, if we now put this into parentheses here, this expression is going to be given by AB, IJ, IJ, V, AB, anti-symmetrized, and then I have AB or V, IJ, anti-symmetrized, divided by epsilon I plus epsilon J minus epsilon A minus epsilon B. Now, this expression is not fully correct. Now, there's a reason for that. If we now look at the operator which we introduced, so let's just wait a little bit so you get time to write down the expressions here. But if you look a little bit more carefully at this phi lambda and phi lambda, which we have introduced, this is actually now a two-body operator, and it has to be anti-symmetrized. So in order to do that properly, since we are now summing over exactly the same single particle states, this needs, when we rewrite this in second quantization, and we are looking at anti-symmetrized operators, this needs, in order to do this correctly, this needs a factor of 1 divided by 4 when we are setting in the operator. So when I did the operations which you saw here, this specific operation here, I was actually not giving you the full story, because this guy here and that guy, when we translate this one into a second quantized operator, then it needs to be anti-symmetrized because we have fermions. So there is in principle another factor 1 divided by 4, because we have to set up the anti-symmetrized sum, or this is actually an outer product between phi lambda and phi lambda. Now this translates into a two-body operator because we are looking at only two particle, two hole states, and it has to be anti-symmetrized properly. If we were looking at one particle, one hole states, we would not need a factor 1 divided by 4. So there is a missing one factor 1 over 4, which we then would have to place back in the final expression. So the final expression is actually 1 divided by 4 and 1 divided by 4 here. And now we can write out the final contribution to the second order perturbation theory. But before we do that, let's now look at the link between full configuration interaction theory and many-body perturbation theory to second order. So if we look at this specific term here, what you will see is that the coefficient which we discussed in FCI, the one which reflects the overlap with a two-particle from a two-particle two-hole state, is now something which is going to be defined in perturbation theory by these terms here. And you see now that you have energy here divided by energy. So the dimension is, this quantity is dimensionless. So in from the FCI calculation, what we had, then from the two-particle two-hole case, we had a term which went like AB, IJ, and then we have a CIJ, AB, and this is multiplied with the integral here, two-body integral. And now you see that when we do this in many-body perturbation theory to second order, MBPT second of two-particle two-hole, this is then going to be given by this factor 1 divided by 4. And then I have a sum over AB, IJ. And now I have IJ, V, AB, anti-symmetrized. And then I have AB, V, IJ, again anti-symmetrized, divided by epsilon I plus epsilon J minus epsilon A minus epsilon B. And now if we single this out, we see that many-body perturbation theory to second order is now an approximation to this term here. So this is an approx. So if I go to third order, I will have a new approximation to the wave function. So remember now that the wave function is defined as a linear combination of all the possible Slater determinants. And in this specific case, what we have now is a term from the two-particle two-hole piece, which we can construct explicitly from many-body perturbation theory order by order. And this is extremely powerful. So this is one of the reasons why I spent some time on this, is I want you to see the links between perturbation theory and FCI calculations. And as we have been discussing many times, if you can do FCI and get the exact states within a given basis, then you could, in principle, run a many-body perturbation theory calculation order by order and see how close the different terms bring you to the exact coefficients. And again, as I said, in project number or the second midterm, you're actually going to look at these kind of expressions. Now, if we collect everything now, so let's just summarize many-body perturbation theory to second order. So delta E0 to second order with Rayleigh-Schrödinger perturbation theory. So we should keep this in mind that now we are using Rayleigh-Schrödinger perturbation theory, and every term, order by order, is something which we can calculate. We know the non-interacting single particle energies. We presumably know how to calculate the integrals. So this could be set up in the form of a table, or alternatively, we could actually have a program which calculates these integrals on the fly. And this is pretty common in quantum chemistry. But what we end up with now is the following. So we have the term, which involves the one particle, one hole guy. So this contains Kj, and then we have an integral here with A, and then we would have our J here. And K and J and I's, they are states below the Fermi level. So this is anti-symmetrized. And then we have the next element, which would now be our state K and A. So we have AK and V, and then we would have IK, anti-symmetrized, divided by epsilon I minus epsilon A. And then finally, we have the term which comes from the two-particle two-hole excitations. So AB, IJ, And then we have the integrals ij, v, ab, anti-symmetrized, ab, v, and ij, anti-symmetrized, divided by the difference between the single particle energies between the two Hall states minus the single particle energies of two states above the Fermi level. So this is roughly, oh, not roughly, it's actually what we get to second order. And then we have now made the interpretation and the links between full configuration interaction theory and many-body perturbation theory. And what we have emphasized is that many-body perturbation theory allows you to calculate these unknown coefficients order by order with only known quantities. And that is the strength of many-body perturbation theory, that it gives you a consistent recipe, order by order, where you can improve the quality of your results. Unfortunately, you don't know whether many-body perturbation theory converges and whether truncation of, let's say, third order is reasonable or not. So we would just leave that to later and to later discussions. What we are going to do now is first to look at a simple example. So we're going to remind ourselves about the example which we introduced in the beginning, but we are going to simplify it further. And we are going to look at the links between many-body perturbation theory with Brienne-Wigner perturbation theory and Rayleigh-Schrödinger perturbation theory. So before we dive into the calculations of diagrams and the way we can then visualize, so the diagrammatic approach, just to anticipate what is coming, is a way by which we can visualize these in terms of simple figures, the diagrams, and then we can interpret these diagrams as a kind of pseudo physical processes. And we will see that after the break. But first, let us now break this down and look at a simple example which hopefully allows you to gain a deeper insight into how we can make the computations and what the results actually mean. So this is a slight iteration of the simple example which we looked at last week. So let's just call this a slight iteration of the simple example. Or a simple 2x2 matrix example. So let me quickly remind you of how we define the Hamiltonian for that specific system in second quantization. So what we had was a Hamiltonian which we defined as a sum over the two states which we have. So these are just, this could be a many-body states, but we would refer to them as single particle states, but they don't need to be that. So we have an epsilon p, and then we have the operators. So this is the term which we label as H0. But now I'm going to change a little bit the interacting piece. And now I'm going to make it so that it's going to simplify the calculations. So in this particular case, we have a strength, which we just call lambda. But now the summation, because in the previous example, what we did was to sum freely over P and Q. Now we are requiring that P and Q cannot be the same. And then we have an AP dagger, and this is multiplied with an AQ here. What we are then going to look at is a two-level system where we have an excited state, we are going to call for E2. This is the exact energy, and E1. That means that when the Hamiltonian now acts on the state psi1, this is going to give us E1, so times psi1. And similarly, when the Hamiltonian acts on psi2, it's going to give us E2 times psi2. Now, as always, we are going now to define the computational basis in terms of the non-interacting piece. So we're going to make an assumption now that there is an H0 which acts on a state phi1, which then gives me epsilon 1. So this is going to be the non-interacting energy, or the unperturbed energy, as we've been calling it. So as I said yesterday, I'm going to use non-interacting and unperturbed as synonyma. And then you can think of this parameter lambda as a perturbation, where you can then tune lambda so that you get a stronger interaction or a weaker interaction. This is also something you would play around with in the second midterm. Then we have phi 2 here, and that is equal to epsilon 2 of phi 2. Then, if we now want to use second quantization, this is going to be given by A dagger 1 acting on a true vacuum, A dagger 2 acting on a true vacuum. And we have obviously assumed that these states are orthogonal of delta Ij. And what it also means is that the exact state now is going to be a superposition of these two states. So the final solution of the problem, this psi 1 or psi 2, are then going to be linear combinations of phi 1 and phi 2. Now, what we're going to do now is simply to remind you of some of the states we're going to set up, and also some of the final expressions we're going to plug into the Hamiltonian matrix. Okay, so let's now do that. So the state, if we now are targeting the ground state, when we diagonalize the Hamiltonian matrix, that is going to be given by the linear combination of these states. And when you diagonalize, these are the coefficients which you get. Now, the Hamiltonian, the way we have written it, is so that when I take the expectation value in the computational basis, this is simply going to give you epsilon 1 here. And that has to do with the fact that the operator which we have chosen, as you can see here now, cannot connect phi 1 with phi 1, because P and Q have to be different. So that simplifies the problem a little bit compared with the example which we looked at last week. Then we also see that if I now take phi 2 of H and phi 2, that is simply going to equal epsilon 2. And finally, if I now look at the cross terms of H, obviously the term with H0 is going to give us 0. So this is simply equal to the term lambda. This is something which I will leave to you guys as a small exercise to see. That means that I can now define a Hamiltonian matrix. So this quantity here now is a matrix. So it's different from the Hamiltonian operator. And this is now just given by this 2 by 2 matrix with epsilon 1 lambda. And then I have lambda and epsilon 2 here. And to find the eigenvalue problem, this means simply that we solve the determinant. We require that that one minus one of these states, EI, can be either the ground state or the lowest lying state or the second state. We have also made the assumption that E1 is smaller than epsilon 2 here. Okay, so this is the problem which we have to solve. And this simply gives us, for the lowest energy, we have an E1 here, which is now simply given by 1/2. And then I have epsilon 1 plus epsilon 2 here. And then I have a minus. And then I have my square root. And in the square root, I can either have epsilon 2 minus 1, or epsilon 1 minus 2. I'm just going to use epsilon 1 minus, because then it's going to cancel one of the terms when I, the term epsilon 2 in front of the expression here, when I'm going to rewrite and perform a Taylor expansion, plus the term for lambda squared. So this is the eigenvalue for the lowest lying state. And now we can do the same exercise which we did last time. So we are going to Taylor expand the square root. And when we Taylor expand the square root, we are going to get an approximation which is going to be compared with Bruyne-Wigner perturbation theory and Rayleigh-Schrödinger perturbation theory. And then what we will see is that Rayleigh-Schrödinger perturbation theory is now going to give us terms, order by order perturbation theory, which are essentially the same as you get order by order in terms of lambda squared divided by epsilon 2 minus epsilon 1 squared. But that's something which we will look at after the break. So now it's time to take a small break. So let me just do that. So before the break, what we did was actually to set up the terms to second order perturbation theory. What we're going to do now, first is to actually go through this simple example and see how we can, through such a simple example, how we can recognize the different terms when we now expand the square root, which we have here. And when we looked at the case earlier, so in the earlier example, what we had was a slightly more modified interaction term, because then we summed freely over P and Q. Now we made a restriction that P cannot be equal to Q, and that gave us an even simpler Hamiltonian matrix, which we are going to which we diagonalized. So let's now look at what this will look like if we now do many-body perturbation theory with Bruyère-Wigner perturbation theory. So this is going to be our first case. So let's just label that one with a 1 here. And then we use the acronym BWPT. And in that specific case, what we had is that the correlation energy for the ground state, in this case, the lowest lying one, and that's why I'm putting a subscript 1 here, is equal to the expectation value for the, and then we have to put an I here to indicate that this is the interaction, because now we have explicitly written an expansion in terms of the interaction. And we know that this one, by definition, is actually equal to 0. Then we have a second order term, which runs like phi of 1, and then I have the interaction piece of the Hamiltonian. I have a phi of 2, and then I have my phi of 2 here, and then I have the interaction piece and phi 1, and this is then divided by E1 minus the non-interacting energy, epsilon 2. Now, in this particular case, each one of these terms, this one and that one, as we saw before the break, gives us simply this variable lambda. And since we have 2 of them, this conspires to lambda squared. Then we have the third order term. And what you will see now is for all the higher order terms, there are going to be overlaps of the following type. So this is a phi 2 here. But then all the intermediates, which we are going to get, due to the fact that we have constructed a very simple operator for the interaction, so this is multiplied with phi 2 of hi and phi 1 finally, and we have a denominator which runs like E1 minus epsilon 2 squared. But due to the fact that we have this kind of intermediate states, which you see here, this one, which now connects only one excluded space state with the same excluded space state. This is the only possibility we have because we have defined such a simple model. Then you see now that this intermediate term, the one in the middle, is always going to be equal to 0. This term is going to carry a factor lambda. This term will also carry a factor lambda. But when I now go to higher and higher order terms, what I will get is actually similar terms. If I go to 4th order, this term will appear squared. If I go to 5th order, this term will appear cubed, etc., etc. So it means that all the higher order terms are actually going to be zeros. So that means that we can just put zeros in. That simply follows from the fact that we have defined a very, very simple Hamiltonian, which now, by definition, gives us, for all the intermediate terms beyond second order, it gives us zeros. So that means that the final energy which we get when we do Brain-Wigner perturbation theory is simply going to be given by delta E1, which is the same as E1 minus the non-interacting energy. And this is given by lambda squared of E1 minus epsilon 2. And it shouldn't come as a surprise now when we now multiply on both sides with E1 minus epsilon 2 and subtract lambda squared. We get E1 minus epsilon 1 and E1 minus epsilon 2 minus lambda squared. And that is the same, I'm going to put that one to 0. That is the same as saying that the determinant of the Hamiltonian matrix minus E1 is equal to 0. So what we see then is that the many-body perturbation theory with Brain-Wigner gives us exactly the same thing we got when we set up the diagonalization problem. And this is also something which we found last time. Now, one thing we could do now, and we are now going to anticipate how this is going to look like if we do want to represent this from a diagrammatic point of view. So let's look at this term lambda squared. And this is given by E1 minus epsilon 2. And it corresponds to us having phi 1, and then the interaction. And then we have phi 2 here. And then we have phi 2. So I'm going to anticipate a little bit the discussions which are going to come. And then we have an E1 minus epsilon 2 here. So as a diagram, the way I can think of this now is a state 1 coming in. The interaction brings us into a state 2. And then this state 2 is then de-excited, and we're going back to the ground state of the system. So from a diagrammatical point of view, we could write it if we want to stay in a kind of pseudo-particle formalism. So we could have a state 1. There is an interaction which we just write with a cross here, which has a strength lambda. We have assumed it's a one-body operator. There is an intermediate state 2 here. And then we have a new interaction which runs like this and has a value lambda. And we have a state 1 here. Now, this would be a diagram in the particle formalism. But we could translate this one into the particle Hall formalism. And in that case, we would then interpret 1 as a state below the Fermi level and 2 as a state above the Fermi level. And that means that if we interpret 1 as a state below the Fermi level, then it's a convention to actually close these 2 lines into a loop. So in the particle Hall formalism, this diagram is going to look like this. So arrow going up is a particle state, and arrows going down are Hall states. So we put labels 2 and 1. So this is how we could represent this diagram in the particle Hall formalism. So this is just to anticipate what is going to come now. However, we haven't done the Rayleigh-Schrödinger perturbation theory. So let's try to do that. So RS perturbation theory, which is case number 2. Now, in that case, if we now look at this to third order, we are going to have E1 now in the perturbation theory, which goes over to epsilon 1. And then obviously E2, if we are targeting that one, but we are actually targeting the lowest line state, goes over to epsilon 2. Now, in this case, delta E1 is equal to, and then we are setting up same perturbative expansion, except that the high order terms differ from Brain-Wigner perturbation theory. This is again by definition equal to 0. But now when I come to second order, I have phi 1, h of I, phi 2, and then I have a phi 2 here, h of I, of phi 1. And this is now divided by epsilon 1 minus epsilon 2. So this is different from the Brane-Wigner perturbation theory, because now order by order, we have something which we can calculate exactly. So if I now go to third order, so this was the second order term, then I go to third order, and I'm going to get something similar to what I had with Brane-Wigner, but the terms are going to be a little bit different. So I have phi 2, I get my phi 2 here, and this is a term which will give rise to 0. This is divided by epsilon 1 minus epsilon 2 squared. And we remember again that due to the definition we made of the interacting piece, this is exactly equal to 0. But then we have a term which is given by phi 1 of h of I, and then I have phi 1 here. But then I'm getting a term here which is going to be equal to phi 1, which looks like the second order perturbation theory term. So I have a phi 2, and then a phi 2 here, and then h of I of phi 1. And this is divided by epsilon 1 minus epsilon 2 squared. Now, this term here is equal to 0. So that is the delta E term when we reorder terms, which is a contribution which comes to first order. And then we have the second order terms coming in there. So the final term is a third order term. So to third order, the only term which survives is actually the second order one, due to this very, very simple example. So if I now set up delta E1 to third order, this is now going to be equal to lambda squared epsilon 1 minus epsilon 2, which is obviously different from the one which we got from Brane-Wigner perturbation theory. So delta E1, and then I'm just going to put BW here. So the E1 now is actually given, or has an approximation, which is epsilon 1, the unperturbed energy, or the non-interacting one, plus lambda squared divided by epsilon 1 minus epsilon 2. Now, let's see what happens when we look at the exact expression and expand the square root. So what we're going to do now is to rewrite that expression we found, the exact one, by solving the second order expression. Then we have a term which goes like epsilon 1 plus epsilon 2. We can single out the term which is given by, so we can have an epsilon 2 minus epsilon 1 here. And then we have a square root of 1 plus x. And x is now given by 4 times lambda squared divided by epsilon 1 minus epsilon 2 squared. And the assumption is obviously that this term, if we now look at this specific term, we actually want 2 times lambda divided by epsilon 1 minus epsilon 2, its absolute value. We want that one to be less than 1. Okay, so if I now do Brane-Wigner perturbation theory, then I have an exact expression. So delta E1 of Brane-Wigner perturbation theory, that is equal to lambda squared of E1 minus epsilon 2 here. Now, if I now look at this expression here, this is something which I can rewrite as a lambda squared of epsilon 1 minus epsilon 2 plus delta E1. And then I can expand that one. But if we look at the expansion of this square root here, let's just look at that one. If I expand the square root, then what I will find then is that E1 is going to be equal to epsilon 1 plus and then I do the expansion, lambda of epsilon 1 minus epsilon 2 here, and then I have 1 minus, and lambda squared of epsilon 1 minus epsilon 2 squared, etc. So I see now that if I pick this term here from the Taylor expansion of the square root, this actually matches what I have with Bruyère-Wigner perturbation theory to second order, actually to third order, because the third order terms disappear. Now, the question is whether this term, which we see here, is going to match what I get with the Rayleigh-Schrödinger perturbation theory. Now, let's now write down the contribution delta E1, and this is the fourth order term from Rayleigh-Schrödinger perturbation theory. So what does that one look like? So let me just bring in two intermediate results. So I'm going to define a term like this one, just to introduce a shorthand, which is equal to phi 1 of h of I of phi 1. Next, I will also define hi of q divided by E0 of h, the interaction part of hi. This is the same as phi 1. And then I have h of I, q divided by E0, which is, and I'm going to define quickly what E0 is, and multiply with E1 and phi 1. So this E0 is actually epsilon 1 minus h0, and q is simply now phi 2, outer product phi 2. So if I use this kind of shorthand, I'm going to get the following expression for many-body perturbation theory to fourth order with Rayleigh-Schrödinger perturbation theory. There's going to be a term, the first term, which looks like q divided by E0, h of I, q divided by E0. So you will see it's a fourth order term in the interaction of h of I. Now, these terms, when you look at, for instance, something like this guy here, that will obviously give rise, since q is defined by phi 2 of h of I of phi 2, so that will always be 0. So this term is equal to 0. Then I have a next term, because now I'm rewriting this term delta E order by order. So we'll have a term which comes like minus h of I, q of E0. There's going to be an expectation value of h of I. So this h of I contains the overlap from phi 1 to phi 1. So this one is actually equal to 0. So the next term as well is 0. And then I have an h of I multiplied with q, E0 multiplied with h of I. So this term becomes 0. And we have three more terms. And it's only one of them which is going to give a non-zero contribution. So the next term is a term which runs like this. So we have an expectation value of q E0, h of I, q E0, and then I have this guy as an expectation value, and then I have a q E0 of h of I. So this one is also equal to 0. Then I have a new term which goes like h of I, and then I have a q E0, h of I in here. I have a q of E0, and then I have an h of I multiplied with a q E0 times hi. This is equal to 0, and this is equal to 0. But then there's a final term which goes like minus h of 1 of q of E0 of h of I, q E0, h of I. And then I have q E0 of h of I. Now, this term here is something which we calculated to second order, and that is simply given by lambda squared divided by epsilon 1 minus epsilon 2. And then these two guys conspire because Q times Q is Q squared, and that is equal to Q. So that gives us just the outer product of phi2 times phi2. And then I have the denominator twice. So this term is just conspiring to lambda squared divided by epsilon 1 minus epsilon 2 squared. So when I add everything together, I get a minus lambda squared, lambda to the power of 4 of epsilon 1 minus epsilon 2 to the power of 3. And this is exactly what we had when we did the Taylor expansion of the square root. So I'm not going to intimidate you by asking you to do the fifth order, sixth order term, because this is not very exciting. But you will see that if you do that, you will get these terms successively. And the Taylor expansion, which we made here, this specific Taylor expansion, is then going to give us, order by order, what many-body perturbation theory with Rayleigh-Schrödinger perturbation theory gives. So this is a very nice example where we can link Breuer-Wigner perturbation theory and Rayleigh-Schrödinger perturbation theory. So Breuer-Wigner, in this particular case, gives us the exact answer, and we have to find the eigenvalues by solving a second-order equation, whereas many-body perturbation theory with Rayleigh-Schrödinger perturbation theory gives us an expansion where the expansion has been made around these energies and as a ratio between the strength of the interaction divided by the energy here. So before we begin with the diagram rules, I wanted to give you a kind of short intermezzo here for when this kind of many-body perturbative approach functions and when it does not function. So if we go back here to this very, very simple example, so one of the things we said is in order to perform this Taylor expansion here, we simply assume that this term here is smaller than 1. So what does it mean for us then? So let's take a closer look. So what we have defined a Fermi level. In this particular case, we simply had epsilon 1 and epsilon 2, but in principle, what we would have is a set of single particle states up to the Fermi level. And this would be the last one, so we would have an epsilon n, and then down to an epsilon 2, and epsilon 1. And then we have the states above the Fermi level, which in our case could be an epsilon n plus 1, etc. The whole thing now is sensitive to this gap. So in our case, we had just epsilon 1 and epsilon 2. So if that gap is very, very small, then clearly we will run into problems if the interaction is larger than epsilon 1 minus epsilon 2. So if we call this for delta particle hole, this is a quantity which we can look up from experiment. So if you look at single atoms like the sodium atom, and we look at the energy, the single particle energy. So you can actually extract from the full energy of the system, if you take the differences between ionized and not ionized sodium, then you could interpret, and this is something which is called Koopman's theorem, which is actually not a theorem, but it's a relation between where you can extract, assuming the same type of mean field, that the energy gap, which results from you knocking out an electron in sodium, is something which you can interpret as the difference between single particle energies. So by doing that, you can then look at this from experiment. If you're doing nuclear physics, this is a quantity which you can extract from the binding energies of a nucleus with either one additional neutron or one additional proton. So you can actually look at an isotopic chain, and you can look at something which is called the neutron gap or the proton gap. that can give you an indication of whether perturbation theory will function or not. So in the example which we had, we were looking at the ratio between only two states, but in general, this translates into, since you have many more particles, this typically translates into the gap between the first excited state above the Fermi level, single particle state, and the last state before the Fermi level. Now, there are many, many interesting cases where you can actually do this experimentally. And the example which I wanted to mention to you is the example of the so-called quantum dots. So quantum dots are actually electrons which are confined to move between layers and semiconductors, where you can set up a potential difference, and you could think of this potential difference resulting in a harmonic oscillator trap. And in this trap, you can then have, let's say here, you could have two electrons in the lowest lying state, but you can have many such states. Normally, this harmonic oscillator trap, which you get, looks like this trap looks like a harmonic oscillator for the lowest lying states. But then, since this is a finite potential well, the particles can actually escape. Now, this harmonic oscillator potential has obviously energies. If you now look at this in 2 dimensions, with quantum numbers nx and ny, which are given by the harmonic oscillator frequency, multiplied with nx plus ny plus 1. So this is in 2 dimensions. And nx and ny, they take values like 0, 1, 2, etc. to infinity, if it is a harmonic oscillator. Now, the thing which is interesting with this type of systems, suppose now that you have 2 particles, then clearly you could define the Fermi level to be represented by all states beyond the first lowest lying state in the harmonic oscillator. Now, what happens when you let these interact is that if your frequency is very large, then your well is going to look like this. It's going to be pretty tight. So you will have the states here where you can fill up the system. You can have 2 electrons here. So we can now think of this as an h bar omega larger than 1. So we make a strong well potential. So this is just the harmonic oscillator potential. Then I can make h bar omega smaller, which means that the well becomes wider. So you will still have this one. So now you can think of h bar omega smaller. There is an interesting thing which happens then. That what happens, so if you look at this spacing, so the spacing here is given by, in using the harmonic oscillator, just by h bar omega. So clearly, if h bar omega is large, you will have a large spacing. However, when you make h bar omega smaller, it means that you will have many more states here. And if you think of the Fermi level like here, then what this results in is that the delta particle hole becomes smaller because h bar omega is smaller. Now, on average, if you calculate with interaction, so the interaction here, since these are electrons, that could be the Coulomb interaction. Now, if we do that, if we set up the Coulomb interaction, what you would expect is when the well has a frequency which is much larger than 1, then the well is getting very tight and the particles are getting closer to each other. What you would expect then is that the Coulomb interaction could play a stronger role. What happens, however, is that the harmonic oscillator expectation value for the energy, which is then given by the harmonic oscillator kinetic energy and just the kinetic energy plus the harmonic oscillator potential, is the one which will dominate the energy contribution. However, when you make the well wider h bar omega is smaller, you have a higher density of states around the Fermi level, your delta pH becomes small, and then the gap between, so this term delta, or the strength for the interaction, with the gap between the state below the Fermi level and above the Fermi level, this can become, delta pH can become very small. But if then lambda is not going to zero at a speed which is faster than the harmonic oscillator contribution, then this term here may become larger than 1. We don't know that before you have evaluated the strength for the interaction, which is given by this constant here. But you see that there is a mechanism that if this one doesn't go quickly to 0, as delta pH becomes smaller and smaller, then we can risk that this inversion, this relation here, tilts in disfavor of a perturbative expansion. So when you're running into a situation like this, where the density of the single particle states is getting larger and larger, so which results in a gap between the states below and below and above the Fermi level is getting smaller and smaller, then perturbation theory may not converge. Stated differently, this means that the ground state of the system, like the one we are studying now, has a strong mixture of one particle, one hole excitations, and possibly also two particle, two hole excitations. So you're going to get the kind of counterintuitive picture where you have a system where the particles on average, so here an electron here and an electron here, on average, the average distance between them is small compared with the average distance here, which is larger. So you would expect that when they're closer to each other, correlation should be important. I mean, the contribution from the interaction. But for this type of systems, it's actually the opposite which takes place if you have the Coulomb interaction, because the Coulomb interaction has an infinite range. And what happens then is that the integrals which involve two particles interacting with each other goes at a slower pace to 0 due to the infinite range of the Coulomb interaction. And what happens then is you reach a point where the kinetic energy goes to 0, because the kinetic energy is proportional to this term in the harmonic oscillator, but where the Coulomb contribution to the energy goes to 0 at a slower pace than what the kinetic energy is doing. And then correlations become very important and perturbation theory breaks down. This is actually something you can make in the lab. So quantum dots are actually called artificial atoms, because you can experimentally tune the size of these potential wells, but you can also experimentally add and remove electrons. So you can make an artificial atom in 2 dimensions, but the system is now trapped by the potential which you are making by setting up electric fields between layers of, let's say, semiconductors. And this case, when the density of states here, single particle states, becomes smaller, no, tighter and tighter, which means that the gap around the Fermi level becomes smaller and smaller, leads to a situation which is a phase transition, actually. And it's called a transition from a normal Fermi system to a Wigner-sized crystallization, because in this particular case, the electrons are going to get kinetic energy, which gets smaller and smaller. So they're becoming more and more localized. But at the same time, the correlations which are induced by the Coulomb interaction, in this case, become more and more important. So this sounds like a kind of contradiction, because the particles are more apart from each other, but due to the fact that the Coulomb interaction has this infinite range, you can actually play around with different potential strengths and monitor the kinetic energy, where the particles are. You can actually almost localize them. And this kind of systems, the quantum dot system, is actually a very active research area in condensed matter physics. and it's also one of the candidate systems for making platforms for quantum computing. This was a long digression, but what I wanted to do was actually to, from this extremely simple example which we had here, this simple 2x2 example, that example conveys a lot of the physics which we can expect. So if the ratio between lambda and E1 minus E2 is less than 1 typically, then this expansion here may become problematic. Okay, so what I wanted to start with now is a discussion of diagrams and diagram rules. And this is going to give us what I like to call a handy way to represent terms in perturbation theory. And you probably see now that it's actually not so exciting to write down all these contributions. At the end, if you want to calculate energies, you have to do that. But if you look at the expressions which we are getting, when you now go to fourth order, we had 1, 2, 3, 4, 5 terms. If we go to third order, we have these terms and that term. And then we have to second order, we have this term. And if we look back a little bit to what we did before the break, when we wrote down the expressions for the second order term, we have to write down all these terms here. Now, the thing with diagrams is that we can simplify this, and we can simplify it considerably. So we will just have one diagram, like for two particle, two hole excitations, we will have one diagram to rule all expressions, and the same with the one particle, one hole graph. So let's now look at the contributions which we get to second order. And I'm going to write down the diagrams, and then I'm going to try to show you how we think when we are setting up these diagrams, and how we can then think in terms of physical processes. So let's now just stay with Rayleigh-Schrödinger perturbation theory. So we're going to stay with that. And let's just remind ourselves about the expressions to second order. So we had a term which is delta E 0 to first order, which is just over phi 0. And we have the two-body interaction, or the interaction term, which is this one. And in this specific case, what we get then, when we plug in the interaction, is, and we have already calculated this previously, so we know that the analytical expression is given by the sum over all states below the Fermi level. And then we had an expression which goes like Ij, V, Ij, anti-symmetrized. So what I've done now is to assume that I'm not doing a Hartree-Fock calculation. I've also baked in the unperturbed term, or the non-interacting term. That is the one which participates in the definition of the correlation energy in perturbation theory. So this term here is something which we have already visualized diagrammatically. And we know that this is something which we can rewrite as 1/2. And then we would have Ij less than F. And if we are thinking of diagrams, then we are dealing with whole lines. So the first term, which is the direct term, is something we would draw like this. So we would have I and J, and then we would have the cross term, where we now have taken into account the Pauli exchange term. And this is given by I and J. And then we have I and J here. Now, when we write this out, that gives us simply 1/2. If I now write out everything, and then I have my Ij, and now I'm not going to put the subscript As, because these are just the integrals, the direct term and the exchange term. So this one is going to be given by Ji. Oh, sorry, it's Ij which goes out. Sorry for that. This is Ij, and then I have Vj1. Now, diagrammatically, what we have when we are now summing over all the states below the Fermi level, this is something which we would write out in terms of this line, this diagram. So we would simply bring together these lines, and that is going to indicate the summation over the i's for all states up to the Fermi level. So this becomes a convention, and then we would have this guy. We put labels, I and j, and then we have a new term, which is the exchange term, which we then would draw like this. We have a state I, and then we have the state j. So that's the exchange variant of this guy here. Now, we don't set in minus signs. We set in minus signs when we are translating this one into an analytical expression. And the same here. Now, we are going to set up the rules, but now I'm just going to draw the diagrams. When we now look at the terms to second order, let's now look at how we can represent these terms and how we can think of the processes which lead to the setup of the expressions. So if we now look at the expression we had for the second order terms, so let's just look at the delta E 0 to second order. Now, the way we can think of this is in terms of a diagrammatic way, and we can set up the whole process as follows. So if we take this expression for the term, for the one particle, one whole term, let's first set up the analytical expression. So we have an AI jk, and then we have a summation over kj v kra. So this is just one way of writing it. And then we have the next term, which is an IA, and then we have a v, and then we have a new term, which is an ij here, anti-symmetrized, like that. And the denominator, epsilon I minus epsilon A. So when we now are setting up these terms, so this corresponds to doing the following. So it's the same as us making a summation over the states lambda, which in our case are one particle, one whole states. We have the ground state of the system. We have the interaction piece. We have our phi lambda and phi lambda of h of I of phi 0 divided by epsilon 0 minus epsilon lambda. Now, the expression which you see here is the one which we want now to link to a diagram. Now, where we started was actually here. So the way you can think of this now is as follows. So you can, if you want to draw this graphically, you could think of us starting with the state. So we would set up the basic state, which we are ending in. And this state is something which we would then define in terms of all these different whole lines. So we would have something like n states below the Fermi level. So now instead of writing this as I, j, etc., I'm going to call this for state 1, state 2, and this is finally the state n. So keep in mind that this is the kind of subdivision we've been doing. So we would have the lowest one, and then this goes up to n minus 1, and then we would have states above here. So this is a state where we are going to end, and we have started in this state, which then also corresponds to a set of whole states. And these are exactly the same as the one we are ending in. So then we would have an H2 and H1. So we are now setting this up as we would have done when we now set up the expression which you have here. Now, the Hamiltonian which we have contains this term Fn, which now has a one-body term. So in the middle here now, we're actually going to have an interaction. So the interaction could be something like this, which can excite the ground state to a two-particle, two-hole state. But then we have also this U Hjorth-Jensen. So this is our interaction V. But then we have the U Hjorth-Jensen here, which is this mean field which we set up. So in the case which we looked at in terms of one particle, one hole excitations, it's actually this guy, which now is being contracted with one of the states which we have here. So you could now think of here having a whole state Hi, which now is contracted with one of the states here. Then in between, we have a new state, or we have this operator phi lambda, divided by the energy denominator, epsilon 0 minus epsilon lambda. And then we have a new interaction, which we just depict like this, plus this other interaction. So what this means, if we now think of this specific state, this one, that would be something like a state which could represent the same whole states, H1, H2, but then one of these is now being promoted to be a particle state. So I'm just putting these two lines here to indicate that this could be a particle state I. And then we have the final H of n. So what I'm doing now is to set up everything in what we call the particle formalism. So what could happen now is that this guy, H of I, contracts with that one. So think of these as particles now, because I'm drawing them as particles. So everything here is now in the particle formalism. I'm just going to stop pretty soon here, and then we will pick up again here next week. So all states are now given as particle states. So that means that we have equation operators acting on a true vacuum. So we could think of this one picking this guy. Then this guy is then contracted with this one, which then finds a partner here again, which is H of I, and it gets contracted with that. All the other ones have to find their corresponding partners because we are dealing with orthogonal states. We have baked that one into the contraction, the commutation rules for creation and annihilation operators. So H1 has then to match H2, Hn has to match Hn, and then except for these kind of interactions which you see here, there is now a chain of contractions which will just give us Kronecker deltas. So that means that at the end, the only term which matters is this one. And then we will keep repeating this for all the single particle states which we have here, which then will interact with this one-body interaction. So next week, we are then also going to look at what happens when these two of these interact with that one. This will create a two-particle, two-hole state. And this is going to create a one-particle, one-hole state. So this is the way you can think of the system. You start in a given state. There is some interaction. This produces an intermediate state for us. Then there's a new interaction, and the system gets de-excited, and you're back to the ground state again. So pictorially, we are going to first set up everything in the particle formalism, but then you will see that this becomes a little bit clumsy. And then we are going to transfer everything over to the particle hole formalism. And then you will just have one diagram, one graph, which you will draw, which is going to represent all the possible contractions which you can set up here. And that's the strength for the diagrammatic approach, that with one diagram, you can actually capture many, many physical processes. So next Thursday, we are going to look at more examples, and we are going to set up the diagram rules. When we set up the rules, what we will do is just to set up the rules first, And then we are going to show mathematically how these rules come out. And then we will have a very compact way by which we can look at a diagram and we can immediately write off the analytical expressions, which is what you would need to compute at the very end. So it's a handy tool for expressing, in particular, many-body theories like copper cluster theory, many-body perturbation theory, Green's function theories. And it gives us a very compact way by which we can also identify physical processes. And some of these diagrams can actually be summed to infinite order, and they will represent specific physical processes. But this is something we will come back to. So it's a powerful tool. Okay, so we're going to stop here today. And we have exercises as well. So if you wish to hang around, I will just keep the window open here. But I'm going to stop the recording now.